Okay, we are going to be on part 2. In this part, we are going to talk about the p-n junction, and the junction is made from the p material which we talked about previously. It is doped with chemical, and then to have the conduction band to have more electrons, and we have the n-type material which is have more holes in the valence band. So that is what we are going to talk about, the behavior of the p-n junction when it is hit with electrons in this photons, and that means when we take a p-n junction and expose it to solar radiation, we want to know how much electricity we are going to get out of it, and that is what we will talk in this section. So we essentially take two pieces of semiconductor metal, one doped with the donor atoms, another doped with the acceptor atoms, and now we bring these two together in their plane faces, and that forms what is called a p-n junction. Like I mentioned before, in practice actually we do not have two materials. They both are manufactured from a single piece of the crystal by varying the doping in different parts of the crystal when it is being grown. The transition region between the p part and the n part is extremely small, and typically it is about 1 micron meter in width. So when you think of it, when they are connected, the transition between the two materials is extremely small. By all practical purposes, they are pretty much one crystal. Then as we talked about, p material has excess holes in the valence band, and n material has excess electrons in the conduction band. And when the contact is made, in fact, we have the excess electrons in the conduction band of the material to cross into the p-type material and annihilate some of the holes which are sitting in the valence band. Consequently, what is going to happen is the charge, which is of course, these are at higher states. There is a net positive charge in the n-type material. An electrostatic potential is set up between these two material parts, and then when once the potential is set up, then these things stop flowing from conduction band to the valence band. And that potential which is set up is shown at the bottom of this figure here, and this is called, when both of them come into equilibrium, then it is called the equilibrium potential. And pictorially what I just said is shown here, and these are, for example, p-type material. These are the holes sitting here, and these are the doped ion cores, and these are boron and phosphorus depending upon what people use. And in the n-type materials, you have the electrons here, and you have the doped ion core. So you bring them together. What we just talked about, you have positive charge built up on the n-type side, and the negative charge is built up in the p-type, and that will give you the equilibrium potential. Now if you want to move the electrons from conduction band to here more than after the equilibrium potential, then you need to have some extra energy to move them across this barrier. And in fact, when you shine a light or increase the temperature, and then of course you are going to have an extra potential, and gives them the current start flowing through the system. And so that is what we could do. For example, this is the conduction band here, and this is the valence band as we talked about, and the energy is given by the essentially delta V, and the force on the carriers is given by the charge multiplied by the energy. So you can see then the holes are moving from left to the right, and electrons are moving from the right to the left, and there is a voltage applied to this. So the applied electric field is going from left to the right. So essentially the positive charge flows to the right, and the negative charge in this particular case flows to the left. So the difference between the current per area from holes and current per area from electrons will give you the total current in the circuit, and that is given by, this is the current density, is not the current, that is the amps per meter square, and this is due to the holes, and this is due to the electrons, and of course the combination of the two will give you the total current in the system. And the voltage in the through this material width is going to vary from the high to the low as shown here with position. So these things start moving beyond the potential which we have shown before by applying the voltage to the system equilibrium, beyond the equilibrium potential. And so when once you do that, then this is the net current which you observe, and then you have the voltage apply, that is multiplied by the current will give you the power essentially, and that is what would happen. Suppose now in this same thing here, except you are showing the energy levels here in the topmost energy level in the valence band and the bottommost energy level in the conduction band here, and this is the equilibrium potential. This is what we have seen. So when you apply the voltage in this particular case, then you see the p type, there is a charge being built, of course higher than the phi naught here. So in a current of course is generated when you impinge the photons on it on the junction. So they essentially the photons will dislodge the electrons from the valence band and create a hole. Then these electron hole pairs will appear, and then that is essentially the basis. Then you get the current which we just seen in the previous slide, and that's essentially the principle for the solar cell. So in the solar cell what we do is we apply the light and we get electricity. The other way, when you apply the electricity and we get the light, is nothing but the light emitting diode. So if a current is driven through the junction by external source like a battery, then you get light coming out of the PN junction, and that's called the light emitting diode, LED light. So that's the reverse of the solar cell. If the two faces of the crystal are perpendicular to the junction plane, then what you get is what's called a semiconductor laser. So essentially what we have here, depending upon the application, either you shine the light on the junction, you get the solar cell, or if you apply the current to the PN junction, you get what's called light emitting diode. And if you change the faces of the PN materials in the crystal, they make it perpendicular to each other, then you get what's called a semiconductor laser. So these three effects can be obtained from the PN junction. So you can use the junction and either you shine a light on it, you get a solar cell. That is what we are interested in this particular application here. So LEDs are essentially same as the reverse of the solar cells. So if you have one technology, you can essentially do the other one very easily. So now once we have created the solar cell, then we model this and try to estimate what the current voltage curve is going to be and how it is different from conventional things what we know in the electrical engineering courses. Thank you.